A locust outbreak looks like sudden chaos, but it begins with a misconception that locusts are a permanently different kind of insect from grasshoppers. They are not. Many locust species spend long stretches of time behaving like ordinary short-horned grasshoppers, dispersed across landscapes, feeding quietly, and causing limited damage. The dramatic swarm phase is conditional, not constant. That distinction matters because it changes how we interpret risk. If we only notice locusts during plagues, we miss the long silent periods when populations are building under the radar. In practical terms, locust danger is less like a permanent enemy and more like a switchable system. Under common conditions, it stays in low-impact mode. Under specific ecological pressure, the same animals reorganize into dense, mobile populations. Understanding this dual life is the foundation for everything else: why control can succeed early, why it fails late, and why the world can go years without major headlines and then suddenly face a regional food emergency. Biologically, locusts sit inside the broader grasshopper family Acrididae, and science does not draw a strict taxonomic wall that separates every locust from every non-locust grasshopper. The practical definition is behavioral. A species counts as locust-like if it can shift into a gregarious swarming phase under intermittently suitable conditions. This is not a trivial naming issue, it affects surveillance strategy. You cannot protect agriculture by tracking a single narrow lineage and assuming everything outside it is safe. Swarming capacity evolved independently in multiple branches, spread across numerous genera and subfamilies. That repeated evolutionary pattern suggests the strategy is adaptive when environments swing between scarcity and temporary abundance. So the locust phenomenon is not a one-off curiosity. It is a recurring ecological design that reappears whenever conditions reward crowding, rapid reproduction, and coordinated movement. For risk planning, this means flexibility. Monitoring must focus on phase change conditions, not just insect identity on paper. The classic trigger sequence is drought followed by sudden vegetation growth. During drought, suitable habitat shrinks, pushing insects into tighter, shared pockets where contact rates rise. Then rain arrives, plants surge, and food becomes briefly abundant in concentrated zones. That combination, crowding plus fresh resources, creates the perfect setup for explosive population growth. But numbers alone do not explain swarms. Inside the insect, neurochemical signaling helps convert density pressure into behavioral change, with serotonin playing a major role in the transition toward gregarious behavior. Individuals that previously kept distance start tolerating proximity, then aligning movement and social responses. At this point, the population is no longer just larger, it is differently organized. This is why locust science emphasizes phase transformation rather than simple multiplication. A high-density population without behavioral transition is one problem. A high-density population that has crossed into gregarious mode is a much more dangerous system, because coordinated movement and mass feeding amplify impact far beyond what head count alone predicts. Once phase change takes hold, life stage dynamics determine how damage spreads. Early on, wingless nymphs form dense marching bands. Because they cannot fly, they advance across the ground in broad fronts, consuming vegetation continuously as they move. For farmers, this stage can feel relentless, repeated wave-like feeding over fields rather than isolated insect patches. Then maturation changes the geometry of risk. Those same cohorts develop wings, and the threat shifts from local marching damage to regional airborne movement. Adult swarms can relocate quickly, settle, feed hard, and lift again, extending destruction across wide areas. This progression is crucial for control timing. When insects are concentrated and wingless, intervention is often more targeted and logistically feasible. After flight-capable swarms form, operations become more complex, expensive, and time-sensitive. In short, the biology creates a narrowing window. Miss the window during nymph concentration, and you may be forced into emergency response across much larger territory. Why are mature swarms so feared? Because they convert local crop stress into moving landscape-scale extraction. Adult locusts are powerful flyers, and their feeding pattern is brutally efficient: land, consume available green biomass, then move on. They do not need to destroy every hectare to trigger crisis. Repeated hits across key production zones can collapse expected yields, reduce fodder for livestock, and destabilize local markets. The human impact then expands beyond the field. Farm income drops, food prices can rise, and vulnerable households lose both produce and purchasing power. In regions already exposed to climate volatility or economic fragility, locust losses can push communities from strain into emergency. This cascading effect is why locust control is treated as a food security issue, not just an entomology problem. The insects damage plants directly, but the deeper risk is systemic. Nutrition, livelihoods, and social stability are all connected to what happens during a few critical weeks of swarm movement. Historical memory confirms that this is not a modern anomaly. Locusts appear in ancient Egyptian imagery and in major literary and religious texts such as the Iliad, the Mahabharata, the Bible, and the Quran. These references persist because outbreaks were not minor events, they were shocks that societies remembered for generations. In agrarian economies with limited storage, transport, and fallback supply chains, losing a harvest could mean famine risk within a single season. Repeated losses could trigger migration, debt spirals, and political stress. So when historical records mention locust plagues, they are documenting ecological disruption with direct human consequences, not merely symbolic fear. This long timeline teaches an important lesson. Locust risk is deeply tied to environmental variability and agricultural vulnerability across centuries. Technology changes the tools, but the underlying interaction between weather, vegetation, insect biology, and human food systems has remained remarkably consistent. The 20th century saw a notable decline in catastrophic swarming impact in many regions, largely because management shifted from reactive to preventive. Better surveillance of breeding grounds allowed teams to detect density buildups earlier. Communication and transport improvements meant warnings could move faster and interventions could be launched before swarms reached full mobility. Agricultural and land use changes also altered some local conditions that previously favored unchecked expansion. The central point is not that locusts became less capable, but that institutions became better at interrupting their phase progression. Early detection changes everything. Controlling concentrated populations before they disperse can prevent the formation of massive airborne fronts. This is the operational core of modern locust management: watch continuously, act early, and coordinate across administrative borders. Without that continuity, gains can reverse quickly, because the insects still retain the same biological capacity for rapid escalation when windows open. Control methods reflect trade-offs. Traditional responses rely heavily on insecticides applied from ground vehicles or aircraft, especially during urgent outbreak windows. These methods can suppress populations quickly, which matters when crops are at immediate risk. But chemical speed comes with concerns: non-target effects, environmental persistence, and exposure risks if operations are poorly managed. That is why biological control approaches have gained importance in integrated strategies. Biological tools aim to reduce locust pressure with more selective ecological footprints, though they may differ in speed, context, suitability, and deployment constraints. No single method is universally best. Terrain, weather, population stage, and operational capacity all shape the right response mix. Effective programs treat control as a systems problem, combine surveillance, forecasting, stage-specific intervention, and method selection rather than relying on one weapon. The objective is dual: protect harvests now while limiting longer-term ecological and public health costs. If systems have improved so much, why do major outbreaks still occur? Because locust control is a vigilance game, and vigilance is hard to sustain during quiet years. Outbreak probability rises when favorable weather sequences return and monitoring or response capacity has eroded. Budget cuts, staffing gaps, political instability, or delayed reporting can all widen the gap between early signal and field action. Once populations cross key thresholds, response becomes more expensive and less precise. This is why experts frame locust management as risk reduction, not risk elimination. You are not trying to erase the species, you are trying to prevent phase conditions from maturing into regional crises. Long periods without visible swarms can create false confidence, encouraging complacency exactly when preparedness should be maintained. In institutional terms, success is paradoxical. When prevention works, it looks like nothing happened, and that invisibility can undermine future prevention. Locusts also have a less discussed identity beyond disaster headlines. They are large, accessible insects widely used in zoology education and behavioral research. Their phase transformation offers a powerful model for studying how environmental pressure can reorganize social behavior and collective movement in animals. In other words, locusts are not only agricultural adversaries, they are scientific windows into rapid, context-dependent change. They are also part of human food history. In multiple cultures, locusts have been consumed and in some places treated as delicacies. This contrast is important because it resists simplistic labeling. The same organism can be a pest under one ecological configuration, a research model in another, and a food resource in a third. Recognizing that complexity does not reduce the seriousness of plagues, but it does sharpen policy thinking, management should be specific to context, stage, and objective rather than driven by one-dimensional narratives. The deepest lesson from locusts is about thresholds and timing. Below threshold conditions, populations remain scattered and manageable. Cross those thresholds through crowding, vegetation pulses, and behavioral transition, and the system can flip into high-impact mode with surprising speed. For agriculture, this means resilience depends on preparation before crisis footage appears, sustained monitoring, shared data across borders, clear response protocols, and rapid action during early concentration phases. For the public, it means understanding that food shocks can originate in ecological dynamics that are invisible until they are already advanced. Locusts are not mysterious invaders that appear from nowhere. They are a predictable potential outcome of known environmental and biological interactions. The challenge is not discovering the threat after it arrives. The challenge is maintaining the discipline to act while the threat is still small enough to contain. If you found this helpful, please like this video and subscribe for more explainers.